Hello, my name is Scott Walensky and I'm one of the technical support engineers here at CD Adapco. Today we're going to review how to use the electrical solver built into STAR-CCM Plus to simulate an accidental electrocution of a human being. As you can see, we have already got an imported geometry of a human being. So we're going to go ahead and begin setting up the physics for this case. First, we go and we define our new physics continuum. We have set that up here, and now we're going to select our models. This is obviously a three-dimensional case. We're going to run at steady state. We're going to simulate the human being as solid with constant properties. We are going to add electromagnetism to the case. It is going to be electrodynamic potential. We're going to do segregated solid energy. We're going to say the human is constant for this case. We're going to turn on ohmic heating to simulate the heating due to the electrocution. And that pretty much sets up our physics. So we're going to close that out, and we now have our physics set up. If you go through the models here, you will see that all of what we just selected is set up. I'm going to change, obviously, the material properties. The human being's not aluminum, so we're going to rename him to human. We're then going to change some properties. I went online and looked up the best I possibly could some of the properties for human flesh, and what we came out is a density of 1010 kilograms per meter cubed, an electrical conductivity of 0.002 s per meter, a specific heat of 3470 joules per kilogram Kelvin, and a thermal conductivity of 0.5 watts per meter Kelvin. I'm going to, at this point in time, save what I've got and continue moving on. Now it becomes time to set up our boundary conditions. There are only two boundary conditions that really become an issue here. We're going to simulate that our human here has used his left hand and touched something he shouldn't have, let's say a live wire. So we're going to change the physics values here. Ambient temperature is going to be constant. Electrical potential we've set here as 110 volts, which is a typical United States source. The electrical resistance we're going to say is none at the source, and the heat transfer coefficient, again looked up from the internet, for a human being is about 2.68 watts per meter squared Kelvin. The other boundary condition that we're going to use here is his right arm. So we go there, and everything on this boundary condition is going to be identical. Go to physics values here. Right hand I should do. And everything's going to be identical except for the electrical potential, which is 0 volts. So in other words, here this person is grounded. We've also done the same thing with his right leg and left leg. We've grounded his feet. So his left arm, obviously reaching out, was unfortunate to touch a live wire, and the rest of his contact points, be it his right arm and his feet, are grounded. At this point in time, we're probably ready to run this case and see what the results sort of look like. So I'm going to select the run. And we can immediately see that there is heat up based on his left hand. You can see where the heat is going. At this point, I will stop the simulation. Here you see the temperature. Obviously it's growing in his left hand where the voltage source is. Looking at the voltage, you can see here most of his body is grounded, but we do have his voltage source at his hand. And you can see the current is also building in his left arm, and as we know, current is what really kills, not voltage. So you can see in an unusual way we have a CFD code that actually uses an electrical solver to accurately predict the trends that can be felt during an electrocution. This can be used in many applications. Thank you very much for your time, and please contact CD Adapco support if you have any questions.